Greetings people, welcome back to Intoxication Calculus. Up to this video I have to confess that you were spoiled with not rigorous enough math, and for this reason today we will look at the most rigorous definition of the limit. Unfortunately, this video will be long, boring and painful, because we are going to look at proofs, a lot of proofs. Unless you are Chuck Norris who proves limits by simply looking at them, I can guarantee you that proving limits with epsilon delta definition of limit will be hard and tedious. So without much wasting of time, let us consider the simplest function y equals x. Let's say we're interested in limit as x approaches 2. Remember that we're not really interested in the value of function at 2, but rather we're interested in the behavior of function as it approaches 2 from two sides, left and right. Thus, for both x and y axis, we're not really interested in the value of 2, but rather we're interested in the small interval of 2 plus or minus certain specific small value. And this difference becomes delta for the x-axis and epsilon for the y-axis. Therefore, the proper rigorous definition of limit will be that the limit will exist if for every epsilon and delta greater than, there is always going to be a certain value, small value, which can be added or subtracted from x in order to get a corresponding small value added or subtracted to the y value. In other words, this condition implies that no matter how close is the value of x to the actual value of a, there is still going to be a corresponding value of L, which is also relatively close to f of x. In order to prove limit using these definitions, first of all, you need to establish that absolute value of x minus a will be less than delta, and after that you need to actually prove that for each of those values there will be a corresponding value of absolute value f of x minus L, which will be less than epsilon. In case of left-hand limit and right-hand limit, there is a certain small modification to the inequality involving delta, because in this case you need to consider only the left side or the right side respectively. Notice also that the inequality involving epsilon does not change because you are not really sure about the behavior of the function in terms of the f of x. So first we'll begin with a slightly complicated example. In this case you can see that even though we're supposed to prove the limit, in reality we're just supposed to prove that if the first statement, first inequality, is satisfied, then the second inequality has to be satisfied as well. The inequality involving epsilon can be actually rewritten in simpler terms. As you can see, it eventually becomes the difference of squares, which is a very familiar pattern. So definitely you can express it as absolute value of x minus 2 multiplied by x plus 2. Strategically, this gives us a benefit because x plus 2 is already present in the first inequality. That's why let's say that x minus 2, the term that is redundant in this case, let it be less than c, and c is just any constant, any value, or simply another unknown variable. This enables us to rewrite the inequality that we have to prove for the epsilon in such a way that the c multiplied by x plus 2 will be less than epsilon. On a side note, our goal right now is not to prove these limits, but rather to find the applicable and appropriate values of epsilon and delta for the proper proof that will follow after this. So we can rewrite the first inequality with epsilon divided over c, because it all follows from simple algebraic manipulation. Next we make an assumption. Let us assume that x will be within interval of 1 from the value of a, which is in this case negative 2. Few rearrangements will result in this new inequalities formed. And using this interval of x, we plug it into the absolute value of x minus 2 in order to determine the applicable value of c. This inequality, it follows that absolute value of x minus 2 is less than 5, and thus 5 is a suitable choice for C. There is already sufficient information for defining delta in terms of epsilon, and considering that we already defined the absolute value of x plus 2 to be less than 1, we have to choose between the minimal value of 1 or epsilon over 5. Continuing with that, now we will move into the proper proof. So as we already defined our interval of concentration to be within 1, and as we already elaborated that the absolute value of x minus 2 is less than 5, we can use this inequality. Also, for the absolute value of x plus 2, we know that first of all it is less than 1 in any case, because the minimum value of 1 and epsilon over 5 will be obviously less than 1 in any case. Also, we can say that implying this condition, the absolute value of x plus 2 will be less than epsilon over 5, because delta x plus 2 will be less than either 1 or epsilon over 5 in any case, because it is less than the minimum of them. So we can finalize our proof by stating that the inequality involving epsilon is correct, because x squared minus 4 absolute value will equal to absolute value of x plus 2 multiplied by absolute value of x minus 1, and considering our inequalities which we already derived, the result will be that it will be less than epsilon. Yes, proving limits rigorously is complex, however, there are few guidelines that you can use. So first of all, before you begin to prove, you need to express delta in terms of epsilon, so you will facilitate your further proof. After that, after you express delta in terms of epsilon, you go into the proper proof where you are acting backwards. You're just coming to the conclusion that you outlined before in the beginning of your proof. Another complex exercise would be to prove one of the limit rules which involves addition. Before you begin, as a reference, you will need so-called triangle inequality, which implies that the absolute value of a plus b is less than absolute value of a plus absolute value of b. I will prove it later, by the way, if you need to look at it. So before we begin, we will need to outline the statement that we are required to prove, which is as follows, where you just have to take the values which are under the lim, subtract them, put it in the absolute value brackets, and make it less than delta, and the same thing for the epsilon inequality. However, you don't have 0 at the beginning. Those are just technical things that you have to do before you even start considering epsilon delta values. So now, using the triangle inequality, you can just simply rewrite it in terms of f of x plus g of x minus l and minus m. By the way, there is a mistake. Yeah, there is a negative sign here and negative sign there instead of positive sign. Anyway, so we can put L and M in the brackets, and after that just rearrange some of the terms exactly like in the triangle inequality, which will result that f of x minus L, absolute value of all that, plus g of x minus m, and absolute value of that. Then they make an important assumption. An assumption in this case will be that those two terms outlined in the triangle inequality will be less than epsilon over 2. And that's completely justified because we can define epsilon. As you probably noticed, this proof is composed of two parts, of two smaller parts, and for this reason we will also consider a smaller proof that we need to show and demonstrate, and in this case it will be the proof for the conditions of limit of f of x and respectively the limit of g of x. The conditions for f of x, for example, will be that if we have this inequality for delta, then the inequality for epsilon will follow as well. So now our task is to prove this specific part. The same proof will apply without loss of generality to the limit of g of x. And we won't write it down here because there isn't enough space for that, so just keep it in your mind. Continuing with that, let us assume that the delta for the overall proof is the minimal value of the two other deltas which appear in the conditions for limit f of x and limit g of x. Respectively, those are delta 1 and delta subscript 2. Using this definition of minimal value, which is very convenient, we can see that in this case x minus a absolute value of that will be less than delta, which is part of the definition. Then it will also follow that it is both less than delta 1 and delta 2 because it is part of the minimum requirement. From here we can see that those are exactly the same conditions as they were outlined in the previous two subproofs, and this leads us to the statement that absolute value of f of x minus L is exactly less of epsilon over 2, which was the second part of those proofs. So by proving that the second statement of those two proofs were actually correct and appropriate, we see that the general proof also is correct and also valid. Similar method of breaking down this larger proof into two smaller subproofs will work for the subtraction and other rules of limits, which were outlined in the previous video. This proof is done. But don't forget about the triangle inequality. If you're interested in this proof, it's a very simple proof. It won't take long. So for triangle inequality, we will just prove the fact that if you square both sides, this inequality will still work. And then if you take the square root of the inequality, you will eventually get the triangle inequality. So consider a plus b squared. Simple factorization will show the following results, and by using properly the absolute value rules, you can see that eventually this a plus b absolute value squared will be actually less than a squared plus b absolute value squared plus 2 absolute value a absolute value b. In this case, the later one is the square of absolute value a plus absolute value b. If you take square root of those two parts, you will get the original triangle equation. Just pure algebra, nothing really exceptional. Yes, indeed, proving those limits may often feel like this, but that's math, you can't do anything. Moving on. This limit will be actually much simpler and much more understandable. First we write out the statement which we need to prove, which in this case follows the same standard format. By the way, this limit is an example of another limit rule, which just shows that limits follow general algebraic rules. Also, when you consider the proof of this limit, notice that when you apply the difference of square rule, you can actually find the connection between the term in the inequality involving delta and the term in the inequality involving epsilon. So as you can see that when you multiply the absolute value of square root x minus square root a by square root x plus square root a, you will actually get the absolute value of x minus a. So using this, you can actually have some significant findings about the possible appropriate values of delta and epsilon. This gives us idea about defining delta in terms of epsilon. Having delta defined in terms of epsilon, we can move on to connecting and establishing the link between the first statement and the second statement. So we have our initial condition, the if part, and now we need to establish the then part. Rewriting delta in terms of epsilon will give us following information. Finally, we come to a really elegant conclusion of everything by simply dividing the whole inequality by square root x plus square root a in order to get rid of that term. And eventually, as you will see just in a few seconds, the result will be that we will have our final inequality involving epsilon proven right there. If you didn't notice, absolute value x minus a divided by square root x plus square root a will actually result in absolute value of square root x plus square root a. Finally, consider the infinite limit. In this case, the conditions for x and delta are not really modified. However, there is a significant change made to y value. Instead of epsilon and the difference between f of x and L, we rather have an infinite value which is larger than any possible positive rational number like m. Here is the last final simple exercise for today, proving the infinite limit. In this case, the first thing that you always have to do is to write out the statement that you need to prove. It's if 0 is less than absolute value of x, which is less than delta, then we will have 1 over x squared, which is greater than any number possible. Now our task is to define delta in terms of epsilon. Simple manipulations with the second inequality that we have to actually prove will give us following results. Then taking square root of both sides will result in absolute value of x being less than 1 over square root m, which gives us a perfect definition for delta. In this case, we can define delta as being 1 over square root m. Right now it's just a matter of going backwards and proving the second inequality of the statement. So we have our first statement, which is already established, that inequality that says that absolute value of delta x is in between delta and 0, and we know that delta is already 1 over square root m, so this becomes clear that absolute value of x is actually less than 1 over square root m, not equal in this case. Sorry, there's a mistake. And eventually that leads us to the final conclusion. Hopefully this video on epsilon delta definition of limits didn't cause any death from boredom. Thanks for attention. Stay tuned with the Intoxication.